Hello, we are Group 8. Welcome to our senior design final presentation. Our project is a 3D portable printer project. And we'll just be going over the progress we've made in the past couple of weeks in this presentation. There we go. All right, so my name is Jack Qualls. I'm the first electrical engineer in the group.
My name is Zachary Yor, and I am the computer engineering of the group.
My name is Michael Doyen. I'm the second electrical engineer in the group.
And my name is Joseph Tuckerman. I'm the final electrical engineer of the group.
Okay, so first we have our design goals. Our design goals are for a printer to have accessible use, meant to be convenient, anyone can use it, have a compact design so that it can be carried around in a portable manner. And we want to make sure that our printer operates at an industry standard, meaning comparable print quality, as well as print speed and print time. We also want it to be user-friendly so that anyone, including professionals, students, and just hobbyists, are able to use our printer effectively. So again, our project features portability. We want on-the-go printing. The main feature of this printer is to be able to use it for rapid prototyping. So whether you're going to a competition or just going to your classes, you want to be able to bring this printer with you, be able to work on the go. It facilitates creation anywhere, anytime, while keeping the precision, like I said, with the industry standard, and reduce the amount of waste and excess filament you'll be using. We want to increase the print time for as long as possible so that we can print uninterrupted, as well as have it print while you're on the go or not near a wall power source, a wall outlet. We want the ease of use so that, again, anyone can use it from in any skill level of 3D printing. The motivations for our project are innovation. We wanted to create a project that really hadn't been done before, something that was unique, but and provided a proper challenge, but that wasn't, undoable for our group. Again, this is something that really hasn't often been seen, so it's breaking some new barriers in the 3D printer industry. Wanted to be accessible. Again, all kinds of people would be able to use our product, and then reliable to make sure that when people did use our product, their prints would be effective and of a good quality. Some of our specifications are shown on screen here, including the power requirements, some spatial requirements, and just the different goals that we set out for the beginning of this project.
Here's our overall hardware block diagram. First starts with our wall outlet charger that goes into our 24-volt battery. And then that branches off into some of our regulators we have on in our voltage divider. We have a Raspberry Pi portion of 3DPP, and as well as the SKR Pico system as well. All this is used in our electronic design.
So one of our first design decisions was ultimately one of our most important, which was deciding which 3D printer control board we're going to use. So we had to decide between the SKR Pico and the Duet 3 Mini 5 Plus. Now they both offer a wide range of compatibility and price ranges, but along these lines, as you can see from the chart, the SKR Pico beats the Duet in almost every field, including price, which is important to us, as well as dimensions, which is, again, very important to us because of our limitations of space and the idea that we want our printer to be portable. Along with this, as you can see on the next slide, the SKR Pico is compatible with the Raspberry Pi, which was a very big feature we were looking for when we were picking a 3D printer control board. This is because we'll be using the Pi or have used the Pi to do various things like run scripts on it to monitor voltage levels of the battery, since this is a portable printer, no batteries attached, or sorry, no wires attached. Along with this, the SKR Pico brings a very fast processing time. And how it does this is by using the Raspberry Pi's microprocessor, as well as it has its own, it's actually another Raspberry Pi microprocessor on the SKR Pico, which enables it to be almost twice as fast as most other 3D printer control boards. And this allows us just to print just as much quicker than the traditional printer. Which again, since we are a battery powered unit, this allows for longer prints.
So here's the comparison between the battery packs we decided for. So first we have the Talent Cell, as well as the QZF electric bike battery. For our project, we decided to go for the Talent Cell because obviously if it's advantage in costs, it's some of its benefits has a high capacitance, amps per hours, the lithium ion technology, and also the ease of integration into our system, since it has few power ports that are easily accessible and also easy to solder wires and connections if you wanted to. Here's our overall PCB design. We have our initial input, and then our 24 to 5 volt circuit is to the right of the input. And then to the right of that, we have our 5 volt to 5 volt 50 milliamp circuit that is used to power the 18 mega as well as our ADC module as well. In the bottom left, that is our ADC module that we designed. And then to the right of that is a voltage divider circuit that Dr. Weeks helped us design. And then to the right, the bottom right, is our AT Mega 328 circuit, which is our microcontroller for our entire project. Here is our PCB design from JLC PCB on the top, and on the bottom is the finalized circuit with every component soldered onto it. As explained before, we have the 24 volt to 5 volt regulator with a constant 2 amps of output. We have our voltage divider that checks for fluctuations in the battery's charge, as well as we have the ADC module attached to get this voltage division circuit to the AT Mega 328 for an I2C communication with the system.
So here are some additional schematics for our PCB designs. On the left, we have the switching circuit, which is used to switch between battery and wall outlet. And then on the right, we have the buck boost converter for the SKR Pico. So for the buck boost converter, it takes a 24 volt input and then it outputs 24 volts as well. And as mentioned before, it's used to power the SKR Pico as well as its peripherals, which are the stepper motors. On the bottom, we have the switching circuit, which, again, as mentioned before, it automatically switches between battery and wall outlet AC to DC power adapter.
All right, so this is about the gantry design. As I went over before in the CDR presentation, a little bit more in depth. The goal of the gantry was to minimize the amount of motors we're using while maximizing the speed at which the gantry was able to move without sacrificing any of the print quality. So we were able to do that by considering a couple different designs. Again, we ended up going with the non-Cartesian gantry, which required less stepper motors, and a pretty unique layout for the belts and the control of the print head. So again, this design minimized the power usage due to it only using 2 stepper motors without sacrificing the precision and speed. In fact, it improved both of those in the long run. Additionally, we had to consider jitter, which is caused by heavy weight on the print head. In this case, it'd be either the print head itself or the lateral linear guide rails, so the one that the print head is mounted to. Because normally you'd have a stepper motor mounted onto that, but with this design, you're able to forego that, instead having it be very lightweight, which reduces the jitter and improves the printer's accuracy overall. It also causes a low center of gravity, which factors additionally into jitter. And due to the minimal jitter, we're able to move the print head around much faster, which increases the overall speed of our printer. Some improvements we made since the CDR presentation were to refabricate some of the thinner components, so the axles that the gears are sitting on, with a higher infill so that they flexed a little bit less, as well as improving the precision of the belts by making adjustments such as tightening them, or again printing different or reprinting some of the components that we had in the initial prototype. So the Z-axis, initially when we designed it, we had some issues with the fluidity of the movement, which I'll play in a video right here. As you can see, it was skipping a little bit. So to remedy that, we came up with a design that added some ball bearings that more smoothly slid along the acrylic rods that are included in the design, as well as including a linear guide rail that would keep the entire build plate what's it called, at a 90-degree angle with the motion of the Z-axis. This overall allowed us to improve the quality of our prints quite a bit, allowing for minimal movement, especially when we got to higher layers. We found that in some of the initial prints, the layer height adjustment wasn't accurate enough, and it would end up smudging a lot of the prints and ruining the quality of them. So it really helped improve that, as well as negated any of the tension caused from the Z-axis belt that was moving the build plate, and that would often cause it to twist and turn up and down, which again was quite bad for the aforementioned reasons. Additionally, we included some plate leveling functions, so springs on the build plate that we could then tighten and loosen to level the print bed. If you know anything about 3D printing, you know that having a level print bed is super crucial to making sure that you get not only a nice build, but proper bed adhesion as well, which, since we are not using a heated print bed and instead going with painter's tape, was incredibly important to us. So adding that feature was a huge plus. So next was the extruder selection. We ended up going with an upgraded Ender 3 hot end. We did this because of the ease of use. It's flexible with almost any printer design. It can also use all the basic filaments. It was relatively low cost and only around $30 for the entire kit, which included the thermistor, insulation, and the heating cartridge. We also chose this because of the thermistor, which worked with the SKR Pico, as well as the 24-volt 40-watt heating cartridge, which is exactly the values that we needed, that was compatible with our design and the PCBs. As for the extruder and the print bed, as we mentioned before, we foregoed the heated print bed and to instead wrap it in duct tape, which we researched and found out was a pretty easy solution to improve your bed adhesion without needing to heat the print bed, which saved us a lot of energy through needing to constantly heat that. Additionally, for the extruder, or the extruder motor, which is feeding the filament into the hot end, we ended up trying to do a custom design. Didn't get the grip on the filament that we needed, so we ended up purchasing a pre-built one. And that did the job perfectly. We also replaced the we replaced the tube, the filament tube that it feeds through to make it a little bit wider. And that way we would reduce the amount of friction that the filament had going into it, because we were getting some jams as well as some other issues, but we ended up remedying a lot of them, and now we get a consistent flow of filament throughout the entire time.
Okay, so here are some of our hardware design challenges that we ran into. So for our SQR Pico power delivery circuit, we needed to design a regulator circuit capable of safely and efficiently meeting the high power demands of the SQR Pico and all the attached peripherals. Also, we did some of the challenges for the switching circuit was to design a circuit that can automatically switch between battery and wall outlet when needed to power the 3D printer. So it's to find an efficient and smart way to switch between those two. Also, for the Raspberry Pi portion of the system, we needed to design a power regulator for the Raspberry Pi and peripherals, since it needed a certain amount of current for the peripherals that we attached. We also ran into some manufacturing inconsistencies when we ordered the boards, such as missing traces and some components were not outlined as they should be, so we had to manually go in and fix them. Also, another challenge was we had to go through the finding low power components, but be able to withstand high input voltage or current. Some of the rectifications we got from the hardware challenges. For the SQR Pico power delivery circuit, we researched and created a buck boost converter to power the SQR Pico. It was referenced and adhered from the data sheets that we found online. For the automatic switching circuit, we researched switching circuits, MOSFETs, and high power path delivery components. We chose the LTC 4421 as the IC for the switching circuit, since this is the best one we could possibly find on the internet for this kind of application. The LTC is capable of handling power demands, high power demands, and has a suitable operating temperature range. The Raspberry Pi portion, after like 3 or 4 iterations, we finally created a design that we are happy with and works to our intentions. And also, since we ran into the PCB manufacturing issues earlier, we decided to go through with a simpler design and have more access for troubleshooting if we need to later on.
All right, so for the overall printer design, we have a couple pictures here of some of the test prints, and you can see the improvement in quality over time, particularly with the cubes in the top left. A little difficult to see because it's a darker, where we printed in black filament, but you can at least very much see from the red print on the left the kind of quality improvement we were able to make in terms of just making sure that the build plate held still. Additionally, with the video on the right, you can see the printer working itself, the good bed adhesion, the filaments sticking to the bed about as well as we could ask for. And yeah.
So going on to the software section, this slide here just demonstrates some of the key software we used. I'm sure most of you are familiar with most of these softwares, but just to go into some of the more probably less known. So we use this software called Mainsail, and that acts as basically our front end for the 3D printer. So essentially you would connect to a WebSocket, and we'll go into more detail into this, but you would connect to a local WebSocket, and it's a front end service where you can control the printer, pick your prints, look at the temperature, move your print head around. In our case specifically, you can look at the battery's voltage powering the printer. Along with this, we decided to use a firmware called Klipper. So Klipper is the firmware of choice we decided to use. And then also we used Vim, which is a simple text editor for the Raspberry Pi. And basically this allowed us to write our Python scripts because the Raspbian version we're using on our Raspberry Pi does not have a GUI. So here you can see what the actual software is doing. So you can see through our block and case diagrams. So essentially, first we'll look at our block diagram. And so the printer starts, and the Python script located on the Raspberry Pi begins reading the battery voltage using the ADC. So from this step, the voltage is then sent to your two on screens. So you'll have Clipper screen, which is a kind of a second firmware we're using, but it's only used for the touchscreen display. So you see the voltage on the Clipper screen, which is the touchscreen, as well as the WebSocket API, which is when you log in with using a mobile device. From there, the Python script will detect, is this voltage in the threshold? So if it is, it'll continue printing. If no, it will send the M0 command, which pauses your print, and a message will display saying you need to charge your batteries, basically. So this is just a little bit more in depth of the software we're using. So again, Mainsail is our firmware, or sorry, Mainsail is our front end. So as you can see here, you can pull this up on any mobile device or your laptop computer, it doesn't matter. You just have to be connected to the same Wi-Fi network. So essentially here, like I said, you can move your print head around, home your printer, as well as pick your prints. And again, as mentioned before, the firmware of choice we decided to use was Clipper. Clipper allowed us to do most of the things we wanted to do, such as using Mainsail and Clipper screen. And Clipper is one of the speediest printing firmwares. Most people will upgrade to this firmware just because of how fast it is. Now, here's just a little bit of the software we're using, just a little bit of the tasks. So first off, we have the code, which is implemented on the Atmega microcontroller. And what this does is it uses the Adafruit library using an Adafruit ADC and reads the voltage value from a divided 24 volt to 5 volt circuit. And what this allows us to do is it reads the battery's voltage, and the Adafruit script will then use a little bit of conversion to update that to actual 24 volts. The Clipper API allows us to connect from a Python script that essentially just sends that code from the microcontroller to the Mainsail as well as the touchscreen display. And some of the software design challenges we faced. So the two were primarily with precision and accuracy and firmware installation configuration. So a little bit more on the precision. It took us a little bit to read through the Clipper documentation. There is a lot of it. So essentially we had to read through the documentation and just fine tune how our stepper motors, like each step, as well as fine tune the resistance in the heating cartridge, just to make sure that the heater was going to the correct temperature. Along with this, just like I said, the firmware installation was a challenge just because of how much we had to install on the Raspberry Pi to get everything running correctly.
So this is just a list of some standards that we adhere to throughout the design process of a project. And it was primarily just PCB standards. This here is a bill of materials for the total cost of our project. Our estimated total is roughly $900, which is right around what we expected to spend.
So just to reiterate, my name is Zachary Yorker, and my primary focuses were on all the microcontrollers as well as the software.
And my name is Michael Doyen. My primary focuses were on the PCB design, on the Raspberry Pi's portion of things, the battery and power consumption. Worked on some of the ADC software as well, and also the printer peripherals that we attached.
My name is Joseph Tuckerman. I was responsible for the other half of the power delivery system, mainly the buck boost circuit for the SKR Pico, as well as the automatic switching circuit.
My name's Jack Wells. I was the electromechanical lead for the project. Mainly, I was working on the 3D CAD design of the printer, as well as finding all the electromechanical parts like stepper motors, and exploring hot-end technology. All right, thank you for listening to our presentation, and along with this, we're submitting the demo video, so please give that a watch. Thank you.